Hey everybody, we're going to get started with chapter 7. I know we already started it in class and live lecture, but I'm going to go over what we covered in class and then finish out the whole chapter. We're talking about chemical reactions and quantities, and I apologize for this not coming out until kind of late. You'll never guess what happened. It's kind of like one of those the dog ate my homework moments. I recorded the video, and then for some reason my mic decided that there should be no audio. So I audit the video before I post it, and there was no audio. So I said, okay, I guess I'll just have to do it again. And between the time that I audited the video and the time I was going to do it again, I pulled a tendon in my pinky. So I was not able to write. It's still a little bit struggle bus, so we'll see what my handwriting is like. But I had to let my pinky heal up a bit before I could do this video. Otherwise, it was going to be a real struggle for me to get through. As it stands, it might still be a little rough. So just bear with me. Um, Stranger things have happened, I'm sure. But it's all right. We're going to get going. So, like I said, we're dealing with chemical reactions and quantities in this chapter. So, we're going to start with reminding you about what a chemical reaction is, what a chemical change is, and move from there to balancing equations, and then get to the reaction types, followed by all the different types of calculations that you can do with chemical equations. So in this first section, we're just going to talk about the chemical equations themselves and how you can identify whether you're observing a chemical reaction or not. Then we're going to talk about balancing equations. So if you'll remember from chapter 3 when we talked about physical changes and chemical changes and all that good stuff, a chemical change occurs when you have a substance that's converted into one or more other substances that are different. They have different properties, different formulas. And there's different things that you can observe, like formation of bubbles or changing color, that show you that a chemical change is happening. A chemical change, remember, is really just saying a reaction. So this table summarizes the types of evidence of a chemical reaction. We have a change in color. The example here is if you have iron nails. If they're exposed to air that has oxygen in it, they will rust. And that rust changes the color of the nail. It's like a brownish red. The same thing happens to cars if you live up north. The second type of evidence that you might see, and you don't have to see all of these, is formation of a gas. That looks like bubbles, so the fizzing. If you've ever seen someone put an Alka-Seltzer tablet into some water, that fizzing is a chemical reaction. If you've made a baking soda volcano, that's a chemical reaction too, and you see the bubbles forming. You usually add some dish soap and some food coloring to make it a little bit more dramatic. Maybe you add food coloring that's red, so it looks like lava. Either way, that foaming is the production of gas. The third type of evidence you might see is the formation of a solid. That solid is also called a precipitate. When you mix two solutions together, let's say you have two clear solutions and you mix them, then all of a sudden you have the formation of a solid, which may be a pretty color like this yellow here. That is evidence of a chemical reaction. The final piece that you might see or feel in this case is a change in heat. If you produce heat or flame, then you're going to see flame or spark, or if you're doing a reaction in some kind of a reaction vessel like a flask or a beaker, it's going to get hot. You're producing heat, it's heating up the flask and the surroundings. You can also have a reaction that requires energy to get started. In that case, the surroundings are going to get a bit cooler, so your flask might get cold. When we write chemical equations, we're describing all of these chemical reactions. The one that's pictured here, we've got some coal here, which is just carbon. It's just lumps of carbon. If you like to grill, or if you go to cookout, then you will absolutely be familiar with this because you're taking carbon and you're burning it in air, which contains oxygen gas. you're creating carbon dioxide, but it's also all that heat and all that flavor. It's getting into that chicken, okay? So grilling, that's chemistry. There are symbols that we use when we write chemical equations. So I'll go over these. I also have a table that's after this slide that shows you kind of the condensed versions of what each symbol means. So whichever one floats your boat, but I'm going to explain it here. When we have a chemical reaction, we've got the reactants, which are like the ingredients, and those are always on the left-hand side. Then there's an arrow, then there's the products. And again, I apologize for my handwriting. I still kind of have a bum pinky on my right hand, and it's in a splint right now, so I can't really write the same, but hopefully it will still be legible. The products are just the result. If you were bringing all the ingredients together to make brownies, flour, maybe some chocolate or some cocoa powder, some kind of leavening agent, liquid, egg, those are the ingredients. The product would be the brownie. The arrow separates the reactants from the products. You can have multiple reactants, multiple products. They're just separated by a plus sign. And in the reaction that I showed you on the page before, there is a little triangle over the arrow. That delta just indicates that you need heat to get the reaction started. So it kind of looks like a Bunsen burner flame. What you'll also see in a chemical equation is the physical states of the compounds. So in parentheses, you'll see an S or an L, a G, or AQ. Those are for solid, liquid, gas, and aqueous. Aqueous just means it's something dissolved in water. And as I promised, here's the table. So if these symbols are very new to you, then it might not be a bad idea to keep this table in your notebook. But for the most part, you've probably seen these before, especially if you've taken high school chemistry. So just make sure that you remember what these states of matter are. Alrighty. Now that we've covered what a chemical equation looks like, and we've refreshed ourselves on what a chemical change is and how we can identify a chemical change, let's talk about balancing chemical equations. In a balanced equation, the number of atoms is the same on each side. So if we have hydrogen and oxygen atoms as reactants, the same number of hydrogens and oxygens should be on the product side. So in this picture, we've got 4 hydrogen atoms and 2 oxygen atoms on the reactant side. We've got the same number on the product side. That's a balanced equation. So the goal when we have to balance equations is to make sure that when we tally everything up, we've got the same number of atoms on the reactant side as we do on the product side for each element. This is a learning check where you can count the number of atoms of each element and just make a table to see how many of each element you have on each side. We did this in the live lecture, but if you weren't there or if you just need a quick refresher, I'll do it for you. The best way to do this is to make a chart. Oops. Don't have 2 reactant sides. Remember, the reactants are on the left side and the products are on the right side. I'm going to write out each element that I see. I see phosphorus and I see bromine. Notice that I'm not writing Br2 or PBr3. Those are compounds. We're trying to keep track of each element and count the number of atoms of each element. On the reactant side, we've got phosphorus and there's this subscript here, which means that I have 4 of them. I have bromine gas, or this is a liquid, and it's Br2. So that means that there's 2 bromine atoms in each of this compound that I have, and I've got 6 of them. So 6 times 2 means I have 12 bromine atoms. On the product side, I have this 4 out in front of the compound. That's a coefficient. It means that I have 4 of the compound. So everything that comes after it, I'm going to multiply by 4. That means I've got 4 phosphorus atoms. And 4 times 3 gives me 12 bromine atoms. So this is a balanced equation. We have the same number of atoms for each element on the reactant side and the product side. We're going to start balancing an equation by doing the same exact thing. We first have to take stock of how many of each element we have on the reactant side and the product side. Then we can start to balance. The only 2 elements in this chemical equation are aluminum and sulfur. On the reactant side, we see 1 of each. On the product side, however, there are 2 aluminum atoms and 3 sulfur atoms, so clearly not balanced. What you do to balance is you start with 1 atom and you look for the lowest common denominator. With aluminum, we've got 1 on the reactant side and 2 on the product side. The lowest common denominator between those 2 is 2. This means that we're going to multiply the number of aluminum atoms by 2 on the reactant side. You place a 2 in front. Never, ever, 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 ever change the subscript. So saying this, good. This, bad. Never change the subscript. After I make a change, I like to make another chart. Now, as you get better at this and you practice, you may not need to make a chart after every time. And I don't always do that. If I just kind of am in the zone, I'll just balance it and then do a final check. But if this is new to you, or you want to make sure that you don't make any mistakes, then you should make a change, then do another table, and then make another change if you're still not balanced. So here, we put a 2 in front of the aluminum, which means that we now have 2. We haven't changed anything else. The aluminum is balanced, but the sulfur is still unbalanced. We're going to go for the lowest common denominator again, which is 3, and multiply the reactant side by 3 for the sulfur. So wherever you see sulfur, you put a 3. This should be our final check. And like I said, even if you don't want to do a table after every single time you make a change, you should at least do an initial table to see where you are, and then a final table to check everything and make sure you're actually balanced. So we already had 2 aluminums on each side. We multiplied by 3 on the reactant side, and we didn't touch the product side. So now we're balanced. If you were asked to write the coefficients or choose which one had the correct coefficients in order from reactants to products, you would choose the letter that had 2 3, and 1. Remember that if there's no coefficient here, it's an implied 1. Let's do another one. We did this one in class 2, so I'm going to go through it a little bit quickly. But sometimes you're going to get chemical equations that are written in words, and you will need to write out the actual equation before you can balance it. So we've got this iron oxide complex, and it's solid, and it reacts with hydrogen gas. Remember, hydrogen gas is one of those diatomic molecules that we talked about in chapter 6. That means that it only rolls in pairs. Hydrogen gas is H2, not just H. When those two react, they produce solid iron and water, which we know is H2O as a liquid. And you'll notice that I put a cursive L there. That's just to make sure that it doesn't get confused as a 1. So it's just a cursive L. You don't have to do it that way, but I think it makes life a little bit easier. Now that we have a chemical equation written down, we can balance what we have. First step is to take stock of how many of each element we have. We've got iron, oxygen, and hydrogen. 3 irons, 4 oxygens, and 2 hydrogens on the reactant side. 1 iron, 2 hydrogens, and 1 oxygen on the product side. So very clearly not balanced. We have lost some atoms along the way. We need to recover those bad boys. I'm going to start by balancing the oxygen. The oxygen is a part of another compound here, and it's going to be one of the more complex ones that we're doing. That just kind of comes from experience to say, okay, I'm going to start here. This looks like a good starting point. So the lowest common denominator between these two is 4. So I will multiply the product side by 4. This time, there is no just straight up oxygen. I have to put the coefficient in front of the compound that has oxygen in it. That's the water. By putting that 4 in front, we've changed more than just the number of oxygen atoms. We've also changed the number of hydrogen atoms on the product side. So we haven't touched the reactant side. We haven't touched the iron on the product side. But we have certainly done something to the oxygen. We now have 4. And now we've got 4 times 2 hydrogens, which is 8. So by balancing the oxygen, we unbalance the hydrogen. So let's fix it. The lowest common denominator between 2 and 8 is 8. That means we have to multiply by 4 for the hydrogen on the reactant side. Stick our 4 in. Now let's do another chart. This can take up a lot of space, but I really want to demonstrate that each time you put in a new coefficient, you change things, and you need to make sure that you're changing what you want. And if you're changing things outside of just the atom you're looking at or the element you're looking at, then you need to make sure that you're accounting for it properly. So we haven't changed the iron or the oxygen on the reactant side, but we now have 8 hydrogens on the reactant side. instead of 2 like we did before. We haven't changed the iron yet, but it's coming. And now we still have the 4 and the 8 for the oxygen and the hydrogen respectively. The last thing we're going to balance is the iron. Lowest common denominator is 3. Put a 3 in front of the iron on the product side, and that should be it. But don't just leave it there. Do a final table to make sure everything is good like you think it is. We've got 3 irons, 4 oxygens, and 8 hydrogens on the reactant side. We just multiplied by 3 for the iron on the product side, and we still have the same number of oxygens and hydrogens as we did before. So everything checks out. If you needed to list the coefficients for these, it would be 1, 4, 3, 4. The last type of example I'll show you is balancing equations with polyatomic ions. This is not harder, you just have to keep track of it a little bit differently. Notice how PO4, which is the phosphate ion, appears on both sides of the equation. You don't see phosphorus or oxygen outside of the phosphate ion. This means that we can keep the phosphate ion together and treat it as one unit. When we're doing our tally, we keep the PO4 together. We've got 3, 1, 1, and 2 on the reactant side. We've got 1, 2, 3, and 1 on the product side. So ain't nothing balanced in this one. So we've got our work cut out for us. Where you choose to start is up to you. But if I see a polyatomic ion, I usually start with that first. We're going to multiply by 2 on the reactant side. That's going to affect our sodium as well as the phosphate. And again, if you're comfortable with kind of balancing by hand and then doing a table at the end, that's fine. So we haven't touched anything on the product side, but the sodium and the phosphate have changed. The next thing I'm going to balance is my sodium. The lowest common denominator between 6 and 1 is 6. So that means where I see the sodium, I'm going to multiply by 6. And that has changed more than just sodium. It's also changed the chlorine. This is why I recommend the table after each time, because you can keep track of all the things that have been affected by placing a coefficient in front of a compound. This time we haven't touched anything on the reactant side, but we did touch the product side. The magnesium is still 3, still 2 phosphates, but now we've got 6 sodiums and 6 chlorines. So far we've balanced the sodium and the phosphate, but the magnesium and the chlorine need some work. They both happen to be in the same compound on the reactant side, so whatever I do to the magnesium is also going to happen to the chlorine. So hopefully that'll work out. Let's look at the chlorine. We've got a 2 and a 6. The lowest common denominator between those is 6. On the reactant side, we're going to place a 3 in front of that magnesium chloride. We do our last table and hope that everything has turned out all right. So here we go. We've got the 6. I'm getting 6 happy here. 2. And then we have a 3 in front here. So now we've got 3 magnesiums and 6 chlorine atoms. On the product side, we haven't changed anything from before, so we can just copy that down. And lo and behold, everything is balanced. The coefficients that we would list for this are 2, 3, 1, 6. That's balancing equations. There are different types of chemical reactions that you may be balancing an equation for. And in this section, we're going to go over those types. This is a list of the types. I'm going to go through each one individually and give you some characteristics about how to identify them. We'll start with combination reactions. In a combination reaction, you have 2 or more elements forming one product. So multiple reactants and one complex product. You may also see this called a synthesis reaction. And I abbreviate reaction RXN. So there's several examples of combination reactions. So you can take a metal and add oxygen and you make a metal oxide. That's a combination reaction. The reverse of a combination is decomposition, where you've got one substance that splits into 2 or more simpler substances. Another way to say it, one reactant, multiple products. And there are a couple of examples here. You've got mercury 2, solid, decomposing to give you mercury liquid and oxygen gas. You're taking one complex reactant and it's being broken down into its constituents, multiple products. The next type of reaction we'll talk about is called a single replacement reaction. In here you have one element swapping in for a different element in a reacting compound. So let's say that you had a strip of zinc. That's a solid. And you dip it into a beaker that has hydrochloric acid. What will happen is you'll see some bubbles form. And those bubbles are hydrogen gas. You'll also start to replace the hydrogen in solution with zinc. So you'll make zinc chloride. It's a clear solution, so no pretty colors there. If you took iron as a solid and put it into copper 2 sulfate, which is a pretty blue color, then you will see copper solid forming, and you'll make iron 2 sulfate. So that's a metal that is replacing something else, usually another metal or hydrogen. in an aqueous solution. You can also have swapping, right? So that's a double replacement reaction where the positive ions switch. So instead of A being with B, as it is over here, you have A's with D. Okay, so they swap partners. Generally speaking, when you see a double replacement reaction, you're also going to see the formation of a solid, which is also called a precipitate, or you're going to see gas formation, and then you're going to form some kind of new aqueous solution. So a double replacement, you see a swapping of the positive ions, whereas single replacement, you just boot one out. The final type we'll talk about in this section is combustion. You're already familiar with combustion, or at least the power of combustion, if you've ever ridden in a car or driven a car, rode the bus, a motorcycle, anything like that. With combustion, you've got a carbon-containing compound burning in the presence of oxygen gas, and you form carbon dioxide and water. You also release a lot of heat as a product. So these are very exothermic reactions. This table summarizes all the different reaction types that we just covered. It wouldn't be a bad thing to put in your notebook. It gives you kind of the generic, combination, decomposition kind of thing with A, B, and C. And then it also gives you real life examples of different chemical reactions. This is the type of question that you'll need to be able to do. Identify each reaction as combination, decomposition, combustion, single replacement, or double replacement. So in an exam setting, you might have this and you'll have, an equation, and you have to choose from the options which equation or which reaction the equation is. I would recommend that you pause it here and give it a shot, and then keep it pushing forward and check your answers. For A, we've got two simple reactants coming together to form one complex product. That's a combination reaction. In B, we've got a solid metal being added to an aqueous solution, and then we're replacing the hydrogen in that solution with the metal. That's a single replacement. In C, we've got a carbon-containing molecule plus oxygen, and we're making carbon dioxide, water, and energy. Only thing that can be is combustion. In D, it looks like we are swapping our positive ions because the lead was with the chloride, now it's with the sulfate, and we formed a solid. This one is a double replacement. Finally, in E, we have one reactant that makes multiple simple products. That's the opposite of a combination, which is decomposition. So I'm abbreviating here to save my sad little pinky finger, but hopefully you can read my chicken scratch type handwriting and you can understand the logic behind how I came to each answer. Now we're going to talk about one more reaction type that doesn't fit in the reaction types that we were just talking about, because you can actually label redox reactions as other types of reactions too. And while I'm at it, oxidation reduction, I will always abbreviate redox, because saying oxidation reduction is a mouthful. So redox reaction is the same thing as oxidation reduction. Redox reactions are really important because they take place in the body and they provide us with energy from the food that we eat. Also, the laptop that you're using, the phone that you're using, And all the other devices that use batteries rely on redox reactions. So redox is really important to the way that we live our lives today. Another example of a redox reaction is rust. So if you've ever lived in a colder climate, or if you've been in a colder climate, you see a lot of cars that are rusted out. That's a redox reaction. A very expensive one to fix. In a redox reaction, you have electrons transferring from one substance to another. And one way that you can remember what oxidation is versus reduction is this mnemonic oil rig. Oxidation is loss of electrons. Reduction is gain of electrons. So oil rig. The way I learned it, Leo the lion says grr, where Leo is lose electrons, oxidize, and grr is gain electrons, reduce. So if you need a little mnemonic, something to help you remember oxidation versus reduction, you can use either one of those, or if you find another one on the interwebs, feel free, as long as you know the difference. When you oxidize, you lose electrons. When you reduce, you gain. I don't know if you've ever seen the Statue of Liberty in person, but you've likely at least seen a picture of it. And you'll notice, one, it's huge, and two, it's green, which is kind of an odd color. The reason it's green is because the copper metal that's in it has been oxidizing, and the color of copper 2 oxide is green. In this reaction, we've got copper and we've got oxygen gas. The copper, when it's a solid, you'll notice here there's a 0. That just means that it's neutral, so it's no charge. But it's oxidized, so it now loses 2 electrons. Loses electrons. So each solid copper atom loses 2 electrons, and it's oxidized. At the same time, we've got oxygen gas, which is also neutral. It's going to gain those 4 electrons that the copper gave up. So the oxygen gas is reduced. Give you one more example. We were talking about single replacement reactions earlier. If you take a strip of zinc and you dip it into a solution of copper 2 sulfate, which I told you was a pretty blue color. See, I didn't lie. You dip it in there, and then you pull it out after a while, you're going to see copper solid on that strip of metal. That's the copper that was replaced by zinc. What happens here is you've got copper ions in solution, so 2 plus, right? They can gain electrons and become copper solid with a neutral charge or no charge. That copper, which again is solid, is deposited onto the strip. The zinc solid, which initially has no charge, will lose electrons. And become the zinc 2 plus ion. The electrons that the zinc loses, the copper will gain and become the solid. So that's another example of transferring electrons and an example of a single replacement reaction. To give you a more biological example, I said that these types of reactions are very important for providing energy for our bodies from the food we eat. There's a coenzyme called FAD. And coenzymes are just think about them as molecules, okay? They're complex molecules that bind to enzymes. And enzymes is just a protein that does chemistry. And that FAD molecule can be reduced by taking on 2 hydrogen atoms, and it becomes FADH2. It can then give those electrons up and become oxidized again. It helps enzymes do complex chemistry that they couldn't normally do. Now, I'm a biochemist, so this stuff is kind of my bag, but we're not going to stay on here because it could get complicated real quick. But just know there are lots of coenzymes that can do similar types of chemistry for redox reactions in the body. And these coenzymes typically they come from the different vitamins that we eat in our food. So vitamin B, folic acid, those types of things that we have in our multivitamins or in the foods that we eat become processed in the body to make the coenzymes that we need to do chemistry. So eat your vegetables. I'm a mom, I can say that. This table summarizes oxidation and reduction. So when you have oxidation, it always involves loss of electrons. What that may look like in terms of a chemical reaction is the addition of oxygen or the loss of a hydrogen. It doesn't have to, but those are 2 examples. With reduction, you're always going to gain electrons. What it might look like with the chemical reaction is loss of an oxygen or the gain of a hydrogen. This slide summarizes that table in words. So if you like words, here you go. If you want exact things to write in your notebook, here you go. You can just pause it on this slide, write it down, and keep it pushing. I'll give you one more example of redox. So CH3OH, it's another way to say methanol. That's methyl alcohol. It's poisonous, so please do not consume it. It is not a good idea. If somehow you do consume it by accident, which I hope never happens to any of you, your body is going to try to deal with it. And it's going to take that methanol and do a redox reaction to form formaldehyde. Formaldehyde is a dangerous byproduct. Formaldehyde is actually used to fix things. So if you've ever done like AP Bio, where you had to do a fetal pig dissection or frog, yeah, formaldehyde is used as a fixing agent for those kinds of specimen. From there, the formaldehyde is oxidized into formic acid. And formic acid is reactive, so it can do damage to the molecules and proteins in your cells. From there, the formic acid is again oxidized, and you create carbon dioxide gas and water, which are not harmful, but all the other intermediates are. And they can cause headaches, and it can cause you to die. So methyl alcohol, you don't want to mess with it. Your body can process a little bit, but it is not recommended. The body is amazing, but don't push it. Okay. Here's a learning check. You need to identify which reactant is oxidized and which one is reduced. Here we've got Ag plus going to Ag0, right? When we don't see anything up here, we can assume it's a 0. No charge, it's neutral. If you go from having a positive charge to no charge, that means that you've gained an electron. And when Leo says grr, that means you have reduced. So the silver ion is reduced. Now, there's only 2 reactants, so that only leaves the chlorine, right? So we already know the answer to A, but let's just make sure we understand it. We're starting with the chlorine ion, which has a charge of -1. That means it's got an extra electron already. When we go over to chlorine gas, which has 2 chlorines together as a molecule, there's no charge. So they must have lost some electrons. That chlorine ion was oxidized. So make sure that makes sense to you, because you'll need to do that kind of thing in an exam setting and for your homework. So 7.1, 7.2, and 7.3 set the stage for identifying the types of reactions you might see, learning how to parse a chemical equation, what each of the parts mean, and we talked about oxidation reduction. We went over what it means to be oxidized, what it means to be reduced, and some of the different ways that redox reactions are important to life as we know it. Now we're going to get to the quantities part of this chapter, and that's the remainder of the chapter. So this might be a good time to take a break, get a snack, rub your eyes a little bit, shake your brain out, and get a calculator. We're going to be doing some calculations, and it's going to be the rest of the chapter. So, buckle up. We're going to start by talking about the mole. The mole is what we use to count particles like atoms and molecules and stuff like that. And it's related to a unit called Avogadro's number, which is named after an Italian physicist who did work and determined that there are 6.02 times 10 to the 23rd carbon atoms and 12.01 grams of carbon. Okay, so that's why it's his number. We can write an equality that says 1 mole is equal to 6.02 times 10 to the 23rd items, which again, for the most part, we're going to be talking about atoms, molecules. We can throw ions in there, but for the most part, it's just going to be atoms and molecules for our purposes, for doing calculations and stuff. So keep this in mind, that equality. And yes, I said equality. I'm also going to say conversion factor. If you were not good with chapter 2, with writing equalities and writing conversion factors from equalities, and using a conversion factor to do math, you'll definitely want to brush up on it. So come to office hours, bring it up in class, rewatch the lectures, all that good stuff. You'll definitely need it from here on out. Since we can write an equality with 1 mole equaling 6.02 times 10 to the 23rd particles, we can also write conversion factors, which, remember, those are the fractions. And these are what we use when we're doing a calculation. What kind of calculation, you ask? Well, I'm glad you asked. We can convert moles to molecules and the reverse, molecules to moles, using Avogadro's number. Here we have a question: how many carbon dioxide molecules are in 0.5 mole of carbon dioxide? With these problems, the first step is to identify the type of problem you have. So you look at what the given information is, and what you're given is a number of moles of carbon dioxide. Now I abbreviate mole and moles, MOL. That's what we're starting with. What we're trying to figure out is how many molecules. Don't abbreviate molecules, because you might confuse yourself with moles and molecules. But the way that you set this up is always the given. So what given information do you have? And then what units for the answer are you looking for? That will help you set up the question type. Now that we've got that, we know our equality. 1 mole is equal to 6.02 times 10 to the 23rd molecules in this case. Now we can write an equation. Starting with 0.500 mole, we need to write a conversion factor from our equality that will convert moles to molecules. That means that we have to cancel out the moles. If we've got moles in the top, we need to put moles in the bottom to cancel. So if you can see this mole down on the bottom. Now we're going to take Avogadro's number and put it on top. Then you multiply across and divide by 1, which dividing by 1 doesn't really do anything, but you'll want to keep in mind that if there is a number other than 1 in the denominator, you will need to divide. When that comes up, as we're doing problems, I'll point it out. Make sure that you can still use your calculator with putting in exponents and writing things in scientific notation, because you'll need to for this section. When you do the multiplication, you should get this. Units are important. We've got molecules here of CO2. Like I said, we can also do the opposite. So this is a multiple choice question. The number of moles of sulfur and 1.8 times 10 to the 24 atoms of sulfur is, and then you got to choose the right one. Our given information is the number of atoms. The question is the number of moles. When we set up our equation, we know that we're going to have to get rid of atoms and be left with moles. We're still using the same equality as before. 1 mole is equal to Avogadro's number. But this time, Avogadro's number goes in the bottom, because we want to know the number of moles. The atoms cancel, and we're just left with moles of sulfur. Your calculator will tell you 2.99 something. But with the correct number of sig figs, which yes, sig figs are back too, you should get B. Now those are just dealing with, molecules, small molecules or atoms. We can also look at bigger compounds. I'm sure you've taken aspirin before. Hopefully my class doesn't cause you to have a headache and need aspirin. If it does, I'm sorry. But when we look at the chemical formula, we can look at it kind of 2 ways. We can look at the subscripts and see the number of atoms of each element there. So there's 9 carbon atoms, 8 hydrogen atoms, and 4 oxygen atoms. But we can also look at it in terms of moles. If we have 1 mole of aspirin, it contains 9 moles of carbon, 8 moles of hydrogen, and 4 moles of oxygen. So if you think about the 1 mole of aspirin like a pie chart, and then what makes up that pie chart is the carbon and the hydrogen and the oxygen. So I explained all that on that slide. This is just a slide that shows in another way the subscripts in a formula and how they relate to the number of moles and the number of atoms. The reason we care about that is because we can write conversion factors to determine how much carbon or hydrogen or whatever other element is in a particular compound. So here in this example, in 1 mole of aspirin, you have 9 moles of carbon. You can write that as a conversion factor. The same thing for the other elements. The second row of this would just be the reciprocal. So you flip it over. I'm going to abbreviate aspirin. And since we can write conversion factors to talk about the number of moles of each element in this compound, that means, you guessed it, we can do some math. How many atoms of carbon are in 0.150 mole of aspirin? Our given information, the number, is moles of aspirin. The question is how many atoms of carbon? So we have to take moles of something and convert that to atoms of something else. We can't just jump straight from moles of aspirin to atoms of carbon. We need to use something in between. The first step is going to be figuring out how many moles of carbon we have. We can't talk about atoms of carbon without knowing how many moles we have. Then we can take those moles and convert them to atoms using good old Avogadro's number. Let's set it up. And again, remember, I'm abbreviating aspirin ASP. We need a conversion factor that talks about the number of moles of carbon in 1 mole of aspirin. We've got 2 choices. We can have the 9 moles of carbon in the top, or we can have the 9 moles of carbon in the bottom. The one that's going to get rid of the moles of aspirin for us is the one with moles of aspirin in the bottom and carbon in the top. The next piece, we're going to be taking the moles of carbon and figuring out how many atoms that corresponds to. That means we're going to use that same equality of 1 mole is equal to 6.02 times 10 to the 23rd atoms and write a conversion factor from there. The moles must go on the bottom to cancel out. Which means that the atoms go on top. So as you can see, we're going from moles of aspirin to moles of carbon to atoms of carbon. When you do this math, you should get 8.13 times 10 to the 23rd atoms. Make sure you can do that math. So we talked about the mole. Now we're going to add on to that concept. Let's say that we have a mole of sodium. That's Na. If we look at the periodic table, you'll see two numbers for it. That top number is the atomic number. We've talked about atomic numbers before. The decimal number underneath is the atomic mass, and it is in atomic mass units. So one atom is 22.99 atomic mass units. But if I have 1 mole of sodium, then I can express the number that I see on the periodic table in grams, and that will give me the molar mass. So here are a couple more examples. If I have carbon, 1 mole of it, I express its atomic mass in grams, and that tells me the molar mass. So this is another equality. We've got from before 1 mole equals 6.02 times 10 to the 23rd things. And now we've got 1 mole of a substance is equal to the number of grams, or the atomic mass expressed in grams. So any element on the periodic table, you know the molar mass just by looking at the periodic table. But what about a compound like lithium carbonate? What you do here is you look at the periodic table and find the molar mass for each element, and then you add all those together. The periodic table that I am using is the one that I've posted on Blackboard for you guys to use with your exams. And there may be an extra decimal place on that one than the one in your book. So that's just a word to the wise. Whichever periodic table you're using, the number of sig figs may be a little bit different. Regardless, I will go with what I've got. When you look each of these up on the periodic table, you should get something very similar to what I'm writing here. You might see 16 for oxygen. That's fine. But we're not done yet. When you look at the compound, there are 2 atoms of lithium, or 2 moles of lithium, and 1 mole of lithium carbonate. So we've got to multiply the molar mass of lithium by 2 to account for that. With the carbon, there's only 1. And with the oxygen, there are 3. You want to do this multiplication first. And then you add them all together. Remember our rules for adding, we care about the number of decimal places. And since the carbon only has 2 places after the decimal, after we do our math, that's the only thing that we can keep. When you add these together, your calculator will tell you this. But we know our last retained digit is right here, so we've got to round. There's a 9 to the right of it, so we're going to round up. So that's one way to write it. That's the equality. You can also write grams per mole as your unit. That's calculating molar mass. It's that simple, I promise. We'll do some more examples in class. We kind of left off here in the live lecture. So we'll pick up here and do an example and then move forward. Now we've got to use that molar mass. If you haven't caught on to the pattern yet, anytime you can write an equality with some conversion factors, it means we're going to be doing some math problems. We were able to convert from atoms or molecules to moles and vice versa. Now we're going to be able to convert from mass to moles and vice versa. We covered molar mass. We said that we can write molar mass as conversion factors, but let me show you what that looks like. So this is the equality. We've got methane gas here, and that's used in like gas stoves and stuff like that, natural gas. The conversion factors we can write would be 1 mole of methane over the number of grams in 1 mole of it. Then you just write the reciprocal. Those we can use to do some math and either convert from moles to grams or grams to moles. So let's try it. Let's say you have a box of table salt. Don't act like you don't know what that is. You see the blue box of Morton's in your grandmama's house if you don't have it yourself. Okay, that box of Morton's salt contains 737 grams of NaCl, which is table salt. How many moles of NaCl are in the box? Now, when you're doing your exam or your homework, you may not necessarily have a nice title that tells you converting mass to moles. You're going to have to figure out what type of problem you have. So again, we look at the given information. What number are you given? You're given 737 grams of NaCl. So we're starting with grams. That's a mass. The question is asking for how many moles. This helps you to set up the problem so you know what you're doing. If you skip this step, then you might not get the problem correct, not because you don't know what you're doing, but because you're trying to set up the wrong problem type. So identify the problem type, then you can figure out what your conversion factors are and actually solve the problem. Here, since we're going from a mass to moles, we're always going to use some kind of a molar mass, and I abbreviate molar mass MM. Because we're talking about sodium chloride, and we have a number of grams of that trying to figure out moles, we need the molar mass of sodium chloride. So you look up on the periodic table, what is the atomic mass of sodium, what's the atomic mass of chlorine, you add them together, and you should get something in the ballpark of 58.443 grams per mole. So our equality looks like this. From there, we can set up our problem. We just need to write a conversion factor. Since we have grams and we want to get rid of them, and grams are in the top, we're going to put grams in the bottom of our conversion factor. That leaves the mole of NaCl to be in the top. And if you do your unit analysis, you'll see you're left with moles, which is what you want. Here you're multiplying by 1 and dividing by 58 point something something something. So again, if you have a number in the denominator, don't forget to divide, because it will be wrong. When you do the math, you should get 12.6 moles. And yes, again, sig figs have come back. We've got 3 sig figs here, and we've got 5 in our molar mass. Since we're doing multiplication and division, that means the number of sig figs matters. We've only got 3. That's our lowest number of sig figs, so that's what we report. This map will help you figure out kind of, I have this given information, how do I get from here to the end point? So let's say that you have the number of moles of an element. Well, with the molar mass, you can figure out how many grams you have. Or if you use Avogadro's number, you can figure out how many atoms you have. So it helps you to figure out where you are and what conversion factors you can use to get from point A to point B to get you to your final answer. Moving right along, we're building here. So each concept from 7.4 onward, you will need to understand. So if you don't understand the concept of a mole, then molar mass probably doesn't make as much sense to you. And if molar mass didn't make sense, then using it as a conversion factor to convert from mass to moles or moles to mass, also big fat question mark. If you don't understand either of those things, then writing mole relationships and using them to do math will also be difficult. So this is one of those times where if one of the puzzle pieces doesn't fit, you can't finish the puzzle. All you got is the corners, but you don't know what you're looking at, and you don't have the box to know that you're building a train. Please let me know. We're going to do the live lecture. We're going to do lots of problems. Don't get lost. If you're someone who watches the lectures and you come to class but you don't really participate because you feel like, oh, well, I have a question that maybe nobody else has, or I don't want to slow people down, don't do that. You're paying tuition too. So make sure that your questions get out there, even if you send me a private message or you send me a message after class using course messages on Blackboard. Make sure that I know that you need help. If you don't feel comfortable coming to me, get a tutor, go to one of your classmates that understands the material a little bit better than you. But do not stay stuck. Okay, now that we got that out of the way, mole relationships. When we talked about chemical equations and balancing chemical equations, we inadvertently talked about the law of conservation of mass. We said that the number of atoms on the reactant side has to equal the same number of atoms on the product side. That means that you can't create or destroy anything, right? Which is the first part of the law of conservation of mass. There's no change in the total mass. If you have 4 atoms of hydrogen and 2 of oxygen on each side, then the mass is going to be the same. And the mass of the products has to equal the mass of the reactants. This is just a depiction of that. So if your grandmama or somebody has some actual silverware that was made with silver, you'll know that it has to be cleaned regularly because it tarnishes. That tarnish is just the silver reacting with sulfur. If you did this as an experiment and you measured out a certain amount of silver and sulfur, and then you combine them in a reaction to make tarnish, if you add those 2 numbers on the scale for your reactants, you should get that same number as the mass of your product. Now, in a perfect world, that's what you'd see. We're going to talk about, kind of percent yield and actual yield versus theoretical yield. Real life isn't that perfect. but you should get something very, very close to it. That's conservation of mass. To figure out how much of something we should be making in the first place, we can still use that chemical equation. So in the previous slide, we were measuring things out and we had the mass in grams, but we also had a chemical equation. And with a chemical equation, you see these coefficients, they're numbers, and here there's an implied 1. We can read that not just as 2 atoms of iron and 3 atoms of sulfur, but 2 moles of iron and 3 moles of sulfur, making 1 mole of iron 3 sulfide. With that said, we can write a mole-mole factor that talks about the ratio of the number of moles for any 2 substances in an equation. Let's say that we wanted to write a mole-mole factor for iron to sulfur. That means we're going to write the number of moles of iron that we have for all of the moles of sulfur that we have. We're just looking at what the chemical equation says and writing it as a fraction. You don't have to create anything. We're just looking at the equation and writing it as a fraction. You can also write the reciprocal. And those are the 2 mole-mole factors for the ratio between iron and sulfur. Let's say that you wanted to do the same thing between sulfur and the iron 3 sulfide. The number of moles of sulfur in the balanced equation is 3 moles. And you make 1 mole of iron 3 sulfide. The reciprocal is also true. Those are mole-mole factors. And they look like fractions, which reminds us of conversion factors. And what does that mean, class? We can do math. Before we do math, I want to make sure that you can actually write the mole-mole factors. So take a second, pause this, and figure out which one, A, B, or C, could be a mole-mole factor to relate ammonia, which is NH3, and hydrogen gas. So please pause it, give this one a shot, and then look for the answer. So here we can do this 2 ways. We can simply write out the mole-mole factors for NH3 and H2, or we can go through each answer choice and kind of rule it out. The first thing we can do, if we're going to go with ruling out any of these answers, is make sure that the compounds we're interested in are the ones that are actually in the answer. You'll notice in C, it's talking about nitrogen gas. We don't care about nitrogen gas, so it can't be that. In A, we've got 1 mole of hydrogen gas and 2 moles of ammonia. Well, if you look at the equation, there's a 3 in front of the hydrogen gas, so it should be 3 moles, not 1. Can't be that. The only answer left is B. So that's a little bit of the reasoning that you can do without even having to write down the mole-mole factors. You will see something like that on your exam. Now we're going to do the math like I threatened. So we've got moles of this iron compound. We're trying to figure out how many moles we can form from 6 moles of oxygen. Always write down what it is you're doing. We've got moles of oxygen gas. and we're trying to figure out moles of this iron oxide. Looks like iron 3 oxide. It's very important to keep track of the units. You can't just write moles to moles because it doesn't tell you moles of what to moles of what. We're starting with moles of oxygen gas and trying to figure out how much of the product we can make. To do this, you need to write a mole-mole factor. I may call it a mole-mole ratio. It's just the same. It's the same thing. It's just a different term. To write the mole-mole factors, you just want to look at the chemical equation. We've got a 3 in front of the oxygen gas, and there's a 2 in front of the iron compound. Then you just write the reciprocal. Those are our two choices. We're starting with 6 moles of oxygen, and we need to choose the mole-mole factor that's going to get us from moles of oxygen to moles of iron 3 oxide. The one I circled is the one that's going to do it because the moles of oxygen are in the bottom, which will cancel out and leave us with moles of iron 3 oxide. Again, there's a number in the numerator, which is the top, and in the denominator, which is the bottom. So you have to multiply across and then divide. When you do that, you should get 4 moles. And again, sig figs. So the numbers that are in the mole-mole factor are exact. We've got 2 sig figs in our given information, and when we're multiplying through and dividing by our mole-mole factor, those numbers do not contribute to how we figure out sig figs. So you have to report 2 sig figs for your answer. Once again, we're building. If you don't understand how to write mole-mole factors and how to choose the correct one to convert moles of one substance to moles of another, you will have problems with section 7.8, which is what we're about to do. So make sure, as you listen to this lecture, as you go through, you try to do practice problems, if you have an issue anywhere along the way, let me know. Talk to somebody. Get a tutor. Do homework with a friend virtually. Be safe. And I don't want you to be up in somebody's face, but get the help you need. This chapter can be really tough for students, but it doesn't have to be, because the biggest issue is you not opening your mouth and saying that you need help. It's okay. If you knew the material, you wouldn't be in the class in the first place. So remember that. All right. So we've built from talking about the mole, converting moles to atoms and atoms to moles. We talked about molar mass and how we can relate the number of moles to a mass, number of grams. Then we talked about chemical equations and how we can write mole-mole factors to relate the number of moles of one substance in an equation to another. Now we can take all of that information and go from the mass of one substance to the mass of another in the same chemical equation. This is a depiction of what you would do for that calculation. So you're starting with grams of A. Let's just do a simple one. Just A goes to B. Okay, this is our equation. You're going to start with the grams of A and multiply it by your molar mass factor for A. That number sign there is where you would put your molar mass. Then you'd multiply that by a mole-mole factor. And it's going to tell you how many moles of B you get for every however many moles of A. The last thing is to convert those moles of B to a mass. You're going to take the molar mass, the number of grams of B, and put it in the top, and 1 mole of B on the bottom. This is what we're going to be doing. Okay? I will break it down. I'll use different colors. It'll be pretty. If you are a colorful, visual type of person, I highly, highly, highly recommend doing your notes with colors and also having color pencils or markers or highlighters or something like that when you're taking your notes, or if you're going back through your notes from the live lecture when we go over this, to use the colors to help you match up each part. This is the same thing that I showed you, only in words. So for those of you who are more verbal and oral learners, here's the words that you can digest. I am a visual person, and I learn by example better than anything else. So let's do a problem together. Suppose we want to determine the mass in grams of ammonia that can be produced from 32 grams of nitrogen gas in the following equation. How do we do that? We identify what we're doing. We've got 32 grams of nitrogen gas, so that's a mass of N2. And what we're trying to figure out is how many grams of NH3, which is yet again a mass. So this is a mass-to-mass problem. Identify what mass you have and what mass you're trying to figure out. So we care about this and this. We do not care about the hydrogen. So just pretend like it's not even there. Pretend you don't even see it. It's just you, nitrogen gas, and ammonia gas. That's it. We're going to need a few things before we can really get started. Since we're talking about masses, we are going to need some molar masses. You're going to need the molar mass of nitrogen gas, which is just looking at the atomic mass for nitrogen and multiplying by 2. Again, my periodic table may have more significant figures than the one in your book, but it's the same process, and you should get roughly the same answer. I'm not going to write out how I get it, because that's just going to take a lot of writing. Just going to give you the final answer. So when you're doing this, you can go back and calculate the molar mass. And if you don't get something that's close to this, then you should, 1, let me know, because sometimes, we all make mistakes. But 2, that means that you might not get the concept of calculating molar mass. And we want to make sure that you get it. All right. Now that we've got our molar masses done, we can start setting up our equation. We're going to start with the mass of nitrogen gas. And the first thing we're due is convert to moles. If we're going from grams to moles, we need the molar mass. The second part of our equation is going to take those moles of nitrogen gas and we're going to convert to moles of ammonia. That's where the mole-mole factor comes in. And it's between the nitrogen gas. Let me actually write it in the B over A. So to be consistent, so we need to relate the ammonia gas and the nitrogen gas using the chemical equation. The last piece is to convert the number of moles of ammonia to grams, because the question is asking for the mass of ammonia. That's where we use the molar mass of ammonia, which we've already calculated. That's, in words, kind of the plan for how we're going to set up this equation. Our starting information, we've got 32 grams of nitrogen gas. Our first bridge, we're going to use the molar mass here. Make sure that you label your molar mass so you know which one is nitrogen gas and which one is ammonia. If you get them switched, you will not get the right answer. We need moles of N2 to move forward, so the moles will go in the top and the grams will go in the bottom. The next part, we're looking at that mole-mole factor. And like I said, we're only looking at the nitrogen and the ammonia. Don't even think about the hydrogen that's in the equation because we don't care about it. It may as well not even exist. We've only got eyes for nitrogen and ammonia. We're trying to cancel out the number of moles of nitrogen. So that nitrogen gas should go on the bottom. We're looking at the equation here. There's no coefficient, so that means we just say it's 1. We look to the equation for the coefficient in front of the ammonia gas. That's a 2. We'll write that as 2 moles of ammonia. That's our mole-mole factor. The final part is taking the number of moles of ammonia and converting to mass. We've got our molar mass here. Again, make sure they're labeled so you know which is which. And this time we're going to put grams in the top, because we want grams at the end, and we need to get rid of the moles of ammonia gas. When you do the unit analysis to make sure all the units cancel except the one you want, the first step gets rid of the grams and leaves you with moles, just like here. The second step is going to get rid of moles of nitrogen gas and leave you with moles of ammonia. The third step gets rid of moles of ammonia and leaves you with grams of ammonia, which is what we want at the end. When you do your math, again, be careful. Make sure that every time you see a number that is not 1 in the denominator, that you divide. When you do all of that and you take sig figs into account, that's how many grams of nitrogen gas you should get. or excuse me, I said nitrogen gas, all confident. That's ammonia gas. It's been a while. About an hour and a half into the video. So, you know, just like you probably tired, like, man, this is long. Same for me. Let's do another example. And we'll do more of these in class together. But I want you to have a couple of examples to go by. This time we have a reaction between hydrogen gas and oxygen gas producing water. How many grams of oxygen reacted? This time we're starting with the number of grams of water, so we know how much product we made, and we're trying to figure out how many grams of oxygen we used to make that water. There's our question boiled down. Just like before, the only thing that we need here from the chemical equation is the oxygen and the water. So just don't even look at the hydrogen. We only care about the oxygen and the water. Believe me, as you start doing all these problems, you'll be tempted to pull in the numbers from the hydrogen gas just because it's there. Don't. The only two things we're concerned with are the oxygen, which we need a molar mass for that. It's about 32. Again, the book may have a slightly different periodic table that doesn't have as many significant figures as the one I'm using. It's the same process though. Now that we've got our molar masses, we need to set up the problem. We're starting with 13.1 grams of water. We need to figure out how many moles. You guessed it, it's the molar mass. We want the grams on the bottom so that they cancel. And the 1 mole on the top. The next part of our equation, we need a mole-mole factor. That way we can go from moles of water to moles of oxygen. We're going to put the number of moles of water on the bottom. And again, that's from the chemical equation. There's a 2 in front, so we write that as 2 moles of water. With the oxygen, there's no coefficient, so we write that as a 1. The final piece is to take the moles of oxygen gas and use the molar mass of oxygen gas to figure out the number of grams. This time the grams go in the top because that's what we want to be left with at the end. And we cancel out the moles of oxygen gas. Again, I'll show you the unit analysis. We're getting rid of the grams and ending up with moles of water. We can use the number of moles of water that we produce to figure out the number of moles of oxygen we use to produce that water. Finally, we're taking the number of moles of oxygen gas and using the molar mass to figure out the number of grams. Make sure all of that matches up before you even touch your calculator, because your calculator will always give you a number. You want to make sure the number you're getting makes sense. After all of that dividing and multiplying and dividing, you should get 11.6 grams of oxygen gas. This is one of the tougher concepts, so it will definitely take practice, and we'll do practice in class together, but you'll need to practice on your own too. Use the homework to practice, and I'll also post practice problems. We're building on top of the mass-to-mass problems that we just did. We're going to add on the concept of a limiting reactant and percent yield. We'll start with the limiting reactant. Now, your book uses the example of making a peanut butter sandwich, which is already sad in my opinion. I love peanut butter, but just a peanut butter sandwich, come on. I mean, look, I didn't grow up rich, still ain't rich. Love peanut butter. We'll eat it off the spoon. But if I'm making a sandwich, I at least need peanut butter and jelly. Or if we're being bougie, maybe some honey. We can do strawberry jam, some preserves. Anyway, that's just me. But we'll use this example for your book, and then I'll give you another one. Just because I'm a little bit of a foodie, okay? If you didn't gather that already. So I'm slightly offended by this peanut butter sandwich that has 2 slices of bread and 1 tablespoon of peanut butter. I get it. We're on a budget. It's a pandemic season out there. There might not be a lot of peanut butter. But can't we aspire for more? A serving of peanut butter is 2 tablespoons. Can't we at least get 2? Come on, Pearson. Alright, I'm going to stop ranting about this peanut butter sandwich. To make this peanut butter sandwich, you need 2 slices of bread, 1 tablespoon of peanut butter. If you have a whole loaf of bread of 20 slices, so that's one of those cheap loaves, like the Sunbeam with the girl with the yellow hat that's got like 90 slices in that one loaf for like $1.05. I've been there. I'm familiar with it. You have one of those loaves of bread and 1 tablespoon of peanut butter, you can only make 1 sandwich. The limiting reactant in that case is the peanut butter, because you've only got enough for 1 sandwich. You make that 1 sandwich, you use up 2 of your 20 slices, you've still got 18 slices left. That's going to be the excess reagent. If you flip it, and you only have 4 slices of bread and a full jar of peanut butter, you can still only make 2 sandwiches, because each sandwich requires 2 slices of bread. You make them 2 sandwiches, you still got a whole jar of peanut butter. Now, in my opinion, you still got a meal, because peanut butter is great. Just make sure you got something to drink, and you'll be straight. But the limiting reactant in this case is the bread, and you have a ton of peanut butter left over. That's the same idea for a chemical equation and when you have different amounts of your reactants. So I'll give you another example, okay? I like breakfast sandwiches. For a good breakfast sandwich, you need a homemade biscuit, not one from a package. I do not want to see a Pillsbury Doughboy anywhere near my biscuit. You need 2 eggs, cooked however you would like, scrambled, over easy, fried, your choice. And you need 1 good sausage patty. Okay? It's got to be it's got to cover the whole biscuit, okay? Don't give me no little half a bite of sausage in my breakfast sandwich because I will hand it back to you by throwing it in your face. I am very particular. And I'm pregnant? Come on. Don't come. Don't come for me. That makes one sandwich. If I have 10 biscuits, 2 eggs, and unlimited sausage, I can still only make one sandwich. As much as putting sausage on a biscuit would be delicious, it's not complete. It does not have all the parts. I've got 2 eggs, and I require 2 eggs for one sandwich. So I'm harping on this. It's a little bit ridiculous. But when you go to do this with the chemicals and chemical equations, you will remember it because you'll be like, yeah, and then my professor, she went on about breakfast sandwiches and like how she likes peanut butter from the jar. I don't know. But this is a limiting reactant. That's what I want. I'm willing to be a little bit crazy for you to remember a concept. You're welcome. In a chemical reaction, the limiting reagent or reactant, I might say reagent, it's the same thing, they're synonyms, is the substance that's used up first. So in our breakfast sandwich example, the eggs would be the limiting reactant, which I also abbreviate LR. It limits the amount of product that can form. Since there's only 2 eggs, we can only make one sandwich, even though we've got all these biscuits and unlimited sausage. Wouldn't that be a dream? Unlimited sausage? You know what I could do with that? Anyway, the reactant that doesn't completely react and is left over is called the excess reactant. So in this case, we've got biscuits galore and we got all the sausage in the world. Those are excess. If we're calculating the moles of a product from a combination of these 2 reagents, we have to figure out the limiting reagent first, and then figure out how much product we'd make from that limiting reagent. Let's do a problem so that it makes a little bit more sense. If we've got 3 moles of carbon monoxide and 5 moles of hydrogen gas, how many moles of methanol can be produced, and what is the limiting reagent? So we've got 2 questions here. 1, how many moles of methanol? And 2, which one of the reactants is the limiting reactant? Now I know I wrote methanol a little bit different. Your book has CH4O. CH3OH is the same thing. That's just how I write methanol. It's the chemist in me. I'm more of a chemist than a biology person, so I'm sorry. What we're really doing here is 2 problems. The first one is figuring out if we have 3 moles of carbon monoxide, how many moles of methanol do we make? Then we have to figure out the question of if I have 5 moles of hydrogen gas, how many moles of methanol will I make? Once we answer those 2 questions, we can figure out which one would make the least amount of product. Starting with 3 moles of carbon monoxide, we need a mole to mole factor. We look at the equation. There's no coefficient, so it's a 1 there. Same for the methanol. We're trying to get to moles of methanol, so that should go in the top. And the bottom, we're going to have moles of carbon monoxide. Those cancel. We make 3 moles. I didn't write out the other 2 zeros, but they're there. Just imagine them in your mind. This isn't the final answer yet. Now we do the same thing for the hydrogen. If I only had the 5 moles of hydrogen gas and unlimited carbon monoxide, how much methanol would I make? We're still going to have the 1 mole of methanol on top of our mole-mole factor. But this time we care about the hydrogen gas. There's a 2 in front, so we write that as 2 moles in the bottom. 5 divided by 2 is 2.5. Now we've got a decision to make. Oops. And we've got to, write the actual product, not hydrogen gas. That's why you should do your unit analysis, so you can catch silly little mistakes like that. It should be methanol. Now that we fixed that, we have a decision to make. Which one of these makes the least amount of product? 2.5 moles is definitely smaller than 3 moles. So the amount of methanol that we produce is going to be 2.50 moles. And that means the reactant that would make that amount is the limiting reactant. This says in words the process that we just did. Converting, if you're starting with the mass of a product or the mass of the reactants, how you would go from that to the mass of your product and figuring out the limiting reactant. It's very similar to the mass to mass. So we did the mass of A to the mass of B. We're doing that only on steroids. I'll show you what I mean. Let's say that we are trying to make silicon carbide. Silicon carbide is a very durable material, and it can handle really, really high temperatures. So it's used as an abrasive, and it's used in brake discs of sports cars. Okay, so when you're braking and you're going really fast, when you brake, there's friction and there's a lot of heat. The silicon carbide is not going to break down. So that's why it's used. How many grams of carbon monoxide are formed from 70 grams of silicon dioxide and 50 grams of carbon? And then there's the chemical equation down here below. Now there ain't enough room for me to solve this on here, so I put the question and the equation on a new slide. This is where you see we have built, okay? We have gone from the bottom to the top of the mountain, all right? Almost the top, actually. There's still one more thing that we're doing after this. We're combining the mass to mass problem type with identifying the limiting reactant. We've got 2 problems to do. The first is figuring out if we've got 70 grams of silicon dioxide, how many grams of carbon monoxide do we make? The second question is if we had 50 grams of carbon, how much carbon monoxide would we make? Once we answer these two questions, we can figure out which one is the limiting reactant, which will determine how much product we make. We're doing a mass-to-mass problem. So we need the molar mass of silicon dioxide, which I've already done. You can do the calculation yourself. You should get something similar to this. You also need the molar mass of carbon monoxide. Let me just write that over again because I want you to actually see it. It's a 28. Okay. We've got our molar masses. Now we're going to set up this problem. We're starting with the 70 grams of silicon dioxide. We first have to use that molar mass of silicon dioxide, and let me try to use the colors, to convert to moles. So I'm not going to write out what each of the steps is doing, but I'm going to use the same colors. So if you did the colors in your notebook, then you should be able to follow along with each of the steps. The next one is your mole-mole factor. We care about the silicon dioxide and the carbon monoxide. We'll put the carbon in the top, carbon monoxide, because that's what we want at the end. And we'll put the moles of silicon dioxide in the bottom. There's a 1 there that's implied. The final part, we're going to take the molar mass of carbon monoxide and use it to convert the number of moles of carbon monoxide. When you do all that multiplying and dividing, you get 65.3 grams of carbon monoxide. We've got to do the same thing for the carbon. Take a deep breath. It's okay. The molar mass of carbon, we don't have to do any calculations for. You just look at the periodic table. And the molar mass of carbon monoxide, we've already calculated. So do yourself a favor, like I said earlier. Make sure you label your molar masses. You never know when you'll need them again. We start off the problem with our known, which is 50 grams of carbon. We need to get those grams into moles. Next comes our mole-mole ratio. Still going to be the same 2 moles of carbon monoxide in the top, but this time we care about how many moles of carbon. And that goes in the bottom. Finally, now that we've got our moles of carbon monoxide, we use its molar mass to figure out how many grams we would make. When you do that math, you should get 77.7 grams of carbon monoxide. Now, we're not done. We have to figure out how many grams we'd actually make if we were to combine 70 grams of silicon dioxide and 50 grams of carbon. You choose the one that's got the least amount of product formed. That's going to be 65.3 grams of carbon monoxide. If the question asked which reagent is the limiting reagent, we would say silicon dioxide is limiting. Wipe the sweat off your brow, it's okay. I know it was a long one. But you need to be able to step through the mass-to-mass problems that we did before and add on the concept of a limiting reagent. The last thing we're going to add to this type of problem, the mass-to-mass, is percent yield. So if you've had a chemistry lab before, you know that what you actually make on the benchtop is different from what you calculate, or what you should get. Should is in quotes if you didn't hear that. When a reaction doesn't go to completion, or you lose some of the reactant or the product, you're going to have a difference in the theoretical yield versus the actual yield. The theoretical yield is calculated. It's using the balanced equation. So the mass-to-mass problems that we were doing, that's how you calculate the theoretical yield. The actual yield is what you actually get. That's experimental. And in a problem, you'd be provided with that. The percent yield is the ratio of the actual yield to the theoretical yield. So you divide the actual yield by the theoretical and multiply by 100%. That gives you your percent yield. Let's do a problem. On a space shuttle, lithium hydroxide is used to absorb exhaled carbon dioxide from breathing air. Very important to remove that because it can be toxic at high levels. And when that happens, it forms lithium bicarbonate. What is the percent yield of the reaction if 50 grams of lithium hydroxide gives 72.8 grams of lithium bicarbonate? This time we've got two numbers and we need to figure out which one is just telling us about the reactant and which one is telling us about the actual yield. Lithium hydroxide is a reactant. So that's going to be what we use to calculate the theoretical yield. .8 grams of lithium bicarbonate, that's the product. So this is our actual yield, and we'll use that when we calculate the percent yield. First, we'll calculate the theoretical yield from 50 grams of lithium hydroxide. To do that, we need some molar masses. For lithium hydroxide, you add together the lithium plus the oxygen plus the hydrogen, and you should get something like this. For the lithium bicarb, you add all those together, it's a bit heavier. Then we set up our problem. Again, we're using the 50 grams of lithium hydroxide. That's our starting material. We use the molar mass of lithium hydroxide and we get the number of moles. We convert those moles of lithium hydroxide to moles of lithium bicarb. They both have no coefficient. I'm going to try writing that again because somehow my 1 ended up looking like a 2. They both have a 1 for a coefficient. So it's a 1-to-1 ratio. Now we're in moles of lithium bicarbonate. We're not there yet because we need the mass. So we're going to use the molar mass that we calculated before. Put that at the top. And you should get something like this. This is our theoretical yield. Now, if you just stopped there, you wouldn't have the right answer because that's not the question. The question is asking about the percent yield of the reaction. All we did was figure out how much we could have made if the reaction went to completion and we didn't lose anything. The percent yield is the actual yield, which we were given in the problem, divided by the theoretical yield, multiplied by 100%. The actual yield was 72.8 grams. What we calculated the yield should be was 142 grams. You divide those two numbers and multiply by 100%. You should get 51.3% for your percent yield. So this combines pretty much all of the concepts from 7.4 when we first introduced the mole up to now. Make sure that each of those pieces makes sense. Otherwise, you won't be able to do the limiting reagent problems that we just did, and you will struggle with the with the percent yield problems if you have to calculate the theoretical yield. The last section in this chapter, we're taking a break from the harder math. Still doing a little bit of math though. We're going to talk about the energy in chemical reactions. Remember at the very beginning, we said that a change in heat can tell you that a chemical change is occurring. Either the change is the flask gets cold, so it's absorbing heat from the environment, or the flask can get hot and you are releasing heat. Well, remember, all that is energy. And the SI unit for energy is the joule. Oftentimes you'll see kilojoules used when we're talking about the amount of energy lost or gained in a chemical reaction. The heat of reaction is the amount of heat absorbed or released during that reaction, and it takes place at a constant pressure. There are several places during a chemical reaction where changes in energy happen. You first have the reactants coming together and interacting. Then you've got bonds breaking apart. So let's give this some context. Let's say that you're making some water, okay? You first have the hydrogen and oxygen gases coming together. That's the reactants coming together and interacting. Then you've got the bonds between the hydrogen molecule and the oxygen molecule breaking. They have to break apart so that they can be rearranged to form water. Now notice, this is not a balanced equation, okay? I just wanted to give you some reference here. So don't try to be like, well, Dr. Hefner, it's not balanced, okay? When you break those bonds apart, you then reform bonds to make a product. And that's another place where energy can change. The heat of the reaction, which is symbolized by the delta H, is the difference in energy between the products and the reactants. In an exothermic reaction, heat is released. So the energy of the products is less than the energy of the reactants. If you're writing the heat as part of the chemical equation, you put the heat on the product side because heat is released. If you're writing a delta H, or you see a delta H with a negative sign, that means that heat is released. It's exothermic. If you have an endothermic reaction, the energy of the products is greater than the energy of the reactants, and you're absorbing heat to make that reaction happen. When you're writing the heat into the equation, it's a reactant. We talked about that delta over the arrow. That's what you would see here if you're writing a chemical equation, because we're adding heat as a reactant. Your delta H is going to be positive for heat being absorbed. We can talk about the delta H, and we can calculate the delta H based on the amount of reactants or products that we use or make. And we can write conversion factors. So if we had water, if we're making water from hydrogen and oxygen, like I used in my example, that process has a positive delta H, which means it's endothermic. If we were to write in where that energy comes into play, it is going to be on the reactant side. We can write conversion factors that talk about how much energy is being absorbed to make the 2 moles of water into hydrogen and oxygen gas. And we can write it just like we do any other mole-mole factor, only in this case we're using energy and relating it to the number of moles of reactants and products. When you do that, you can actually calculate the amount of energy absorbed or released during the course of a reaction. In this case, we're trying to figure out how much heat is released when nitrogen and hydrogen react to form 50 grams of ammonia. Notice we've got a negative delta H here. So that means it's an exothermic reaction, and that the heat is a product because it's being released. You can rewrite this equation to include the energy from the reaction. So we added that on the product side because the heat is being released. Now we can look at what we're being asked. How much heat in kilojoules is released when nitrogen and hydrogen react to form 50 grams of ammonia? So we need to go from grams of ammonia to moles of ammonia, because we can't do anything with grams. We can't take grams and look at the chemical equation. The chemical equation is talking about moles. Once we have moles of ammonia, Then we can use a conversion factor with the delta H and NH3, the number of moles. And that will give us the energy released from this reaction. To go from grams to moles, you need the molar mass of ammonia. We already calculated that before, so I am not going to go through the trouble. That's the molar mass. We start with the number of grams. We convert that to moles using the molar mass that we just figured out. Then we need a conversion factor that talks about the amount of heat that's generated in relation to the number of moles of ammonia. We need to cancel out the moles of ammonia, so we look at the equation and we use the coefficient that's in front of the ammonia. That's a 2. We said that 92.2 kilojoules of energy are released when we make 2 moles of ammonia. You do all your canceling and you realize, okay, great, we're going to have kilojoules at the end. You do the math, multiplying and dividing and all that good stuff, and you should get 135 kilojoules of energy released. For the billionth time, if there's any part during the course of this lecture that doesn't make sense to you, it's going to be very difficult to do the problems towards the end of the chapter. So we need to make sure you have the basics down. We will cover them in class together, but we're also going to focus a good amount of time on doing these big combination problems to make sure that you got it down. I'll give you a little bit of a link to health. So cold packs and hot packs, very close to my heart at this point in time. Not sure if the Lord orchestrated that, thank you. But when we talk about cold packs and hot packs, we're talking about chemistry. So the ones that you hit them or you smack them or something, and then all of a sudden it feels cold or hot. Those are the ones we're talking about. For a cold pack, you have solid ammonium nitrate, and it's in its own little compartment, and then you've got water in another compartment. Then you hit it or you squeeze it, and they break open and they mix. It's an endothermic reaction, so it's actually going to get cold, and that makes the cold pack a cold pack. The opposite is true for a hot pack. You've got solid calcium chloride that is separated from water. When you hit that, the compartments break open and the calcium chloride is dissolved in the water. And that is an exothermic reaction that makes the pack hot. This is the concept map for Chapter 7. It relates all the different terms that we talked about and all the different calculations and things that we did all throughout the chapter. So if this helps you to kind of make sense of things, by all means, look at it, print it out, talk it through. I thought I had reminders at the end, but I guess not. So for reminders for this one, you've got that Chapter 7 check-in that is due on Blackboard. Make sure that you get that in on Sunday, which is October 18th. And again, I apologize for this video coming out so late. I had a couple of things preventing me from writing, so the video would not have been possible in the way that I normally do it if I didn't let my hand heal up some. You also have Mastering Chemistry assignments, which are not due until the 25th because we have not finished covering Chapter 7 yet. But do what you can and bring your questions to class in office hours this coming week. You've got Exam 3 coming up, which covers Chapters 7 and 8. So only 2 chapters this time. And that will be at the end of the month. It will be available October 28th in its own little folder in the course content section. And you will have until Friday, October 30th at 11:59 to begin the exam. I'll give you more details as we get closer. That's all I got for you. I know it's kind of a big chapter, quite a long lecture, but if you hung out through the whole thing and took notes and stuff, good for you, because this is a long time. We'll do some examples in class and make sure that everything is ironed out. So bring your questions if you have any, and we'll make sure you're squared away. Until I see you in class, please stay safe. I'll see you soon.